Hi, Mrs. Stanley here. This is Unit 2, Lesson 3, Understanding the Derivative and Linear Approximations. That's going to be a new vocabulary word for us today. Let's first just read what we have here at the top. There are times when we are interested in finding the effect of small change. For example, how is the revenue at your local theater affected by a small change in the ticket price for a movie? We can explore an application of the tangent line to a function called the linear approximation. You have already seen that a curve lies very close to its tangent line near the point of tangency. So this is what we've already talked about, that the slope of the curve is pretty close to the exact same as the slope of the tangent line near the point of tangency. If you zoomed in repeatedly on the graph of f at the point a, f of a, the function will appear to be linear. When you have zoomed into a sufficiently small neighborhood around the point of tangency, it would be difficult to distinguish the function from its tangent line. This property of differentiable functions is commonly referred to as local linearity. So first, let's just clarify. Sufficiently small, that sounds very subjective. What is sufficiently small? How big of a space is that? Well, the thing is, it depends on the function. Let's look here at an example. This is the graph of the sine function. We are used to seeing this graph, right? But actually, this graph here on the right is the exact same graph. It's just zoomed in. Look at the x-axis. It is zoomed into such a tiny space that it looks like a straight line, but it's actually the exact same graph. Notice the two functions. So this is what we're saying. Zooming in to a sufficiently small neighborhood, that just means keep zooming in until you see a straight line. That's all it means. There's not like a set defined like, oh, you need to zoom 10% or 100% or any certain amount. It's just until you see a straight line. Because basically what's going to happen is once you get zoomed in far enough in a certain area, that area will look like a straight line. So let's look at example number 1 here, the one we just talked about with the sine function. You could pull up your graphing calculator or Desmos.com to do this yourself. In this particular visual example that you have, it is zoomed in 4 times from the original. So they just zoomed in 4 times. So can you estimate the slope of this portion of the sine curve? So looking at the graph right here, could you decide what do you think the slope would be? Now notice we're just estimating. We're not trying to get the exact. And it looks to be like there's a point about right here, 0.05 and 0.05. And so I feel like that's a pretty good estimate that it appears to be a slope of 1. Now, since it's an estimate, if you have a different answer, as long as we're reasonably close to each other, it's an estimate. What can you say about the slope of the tangent line at x equals 1 on the function y equals x? Okay, well, think about it right here. If you drew this tangent line, what would you think the slope probably is? It looks pretty close. My pen is so thick compared to their little graph, but you can tell that that's what's happening there on the graph. So it also has a slope of 1. Here we go. The slope of the tangent line at x equals 0 is 1 on y equals sine of x. Okay, so then notice C, write the equation of the tangent line for y equals sine of x at x equals 0. Well, we already know at x equals 0, y is also 0, because think about it, our point is right there at 0, 0. And we said that we think that the slope is 1. And so we're going to have y equals 1 times x minus 0 plus 0, which we all know is just y equals x. Okay? So right now you might be thinking, okay, what's the point? We're just talking about the idea of local linearity. So let's go on to some more examples and go a little further. Notice the topic here, estimating derivatives at a function at a point. Sketching tangent lines. In each figure, basically, I want you to take a straight edge of some sort, even if you're using a computer device, however you need to do it, you're going to draw a straight line. You're going to find the tangent and estimate its slope for each one. Okay? So, for example, here at point A on graph A, let's draw in the tangent line. Okay, here is my tangent line. Again, this is an estimate. So I will tell you right now, it is very difficult. That the chances that all of us would get the exact same answer are probably about the chances of winning some lottery. They're not very high because, one, we're using digital tablets, we're using paper and pencil that was photocopied and printed out and all that sort of stuff. And drawing the tangent perfectly is very difficult, even if you had the exact conditions that were necessary. So you're just estimating, okay? Keep that in mind. So here, if I were trying to choose a point, I would estimate that the slope, I'm just going to put m of a so that we know which one I'm talking about. If I can find a point on this line, then I can just estimate. I might have moved my line. It's a little bit hard to do this, but if I look like 1, 2, 3, 4, 5 and go over 1, that's pretty close to that point. And so I'm going to say that this has a slope of 5. Okay. For B, that one is actually at least a little bit easy. The slope of B is 0. C is going to be another one that's going to be difficult, and that's okay. Just do your best. Oh, that was bad. I don't want to do that bad. Can't seem to draw this straight line. Okay, so this one, I'm here at the point 1, 1. If I go over 1, it looks like there's a point right there. I'm going to call it -2. Again, these are estimates. If you got something different, please, by all means. If you're like reasonably close, it's fine. Let's see. We're going to do the same thing. Okay, I'm not going to do all of these here in the video. Go through and try to make a line and see what you think the slope is, and then I will come to any key points and we will discuss them. So I'm going to pause. I want you to pause and do at least part B, A, B, C. When you finish B, push play and check your answers, okay? I've given you plenty of time to pause now. So do B, estimate the slopes of A, B, and C as tangent lines, and then come back and look. Okay, for A, I've got -2. Interesting thing to notice, this is a linear line basically. So it's going to be the slope of the line, okay? If I could draw a straight line. So if you have a linear function, or that piece of a piecewise function is linear, it's going to be the slope of the line. Now, what do you notice about B? You could make a line there. You could make a line there. I can do a lot of lines through that point and not technically be tangent. This is a strange place on a graph. This is actually that the tangent does not exist, okay? Let's now go to C. Try C, pause, come back to it. You could even try C and D and then pause and come back to it, okay? 3, 2, 1. Okay, here's C. M of A is -1/2. M of C is +1/2. Notice it's basically like they're opposites of each other. And then B does not exist. This is very similar to what we had up here for B on graph B. There is a word that I want to call this for you. These could be called corners. I should say there's 2 words. Corners or cusps. I honestly am not really familiar with how are either of these words specifically designed, because they're not like formal vocabulary words. They're just common slang words that you will hear. And so I just want to let you know that we can say something is a corner or a cusp. And when that happens, does not exist for the tangent. And think about it. There would also not be a derivative. If the slope of the tangent doesn't exist, there is no derivative, okay? And then also, just to give you a little bit of a visual, I will point out, we could imagine that if we kept doing the slope, eventually this could be basically a vertical line, and that would be does not exist as well. So it would make sense that that could happen. So go to D and give your answer and see what you get. All right, the slope of the tangent line at A does not exist because it's a vertical line. It's undefined. So think of it in that way. In many ways, something that we used to call undefined, we're saying does not exist. They're related to each other, right? Remember the vertical asymptotes? We said the limit doesn't exist, etc. So let's come to number 3. The position of the tangent line relative to the function it models. that's important, relative to the function it models, depends on the concavity of the function at the point of tangency. Throughout the course, you will be required to explain, justify, and defend your knowledge using proper terminology and precision. The graphs from example number 2 above, oh, I skipped the word use. Use the graphs from example number 2 above to complete the following statements. So we're going to use these graphs to help us figure out these statements, okay? It may be that sometimes we have to think beyond the graphs, but I think everything is visible to us. So here we go. When the curve is concave up, the tangent line lies where? It's asking us, where does the tangent lie? Now think about concave up. For example, in graph A, this entire thing is concave down. Concave up, if you wanted to, you could make a note on your paper. It looks like this. Over the word concave up, I just drew an example. It doesn't have to be that drastic. It could be very minimal. Okay? It's like a smiley face. It's concave up. The tangent line is going to be below the curve. Think about that right here on graph A, point B. If the parabola was the other way, our tangent would be down here, right? So just keep that in mind. And then the opposite, when the curve is concave down, meaning it goes this way, the tangent line lies where? Above the curve. So these are opposites. It makes sense. Sorry about my bad handwriting there. Except at the point of tangency. Remember, the point of tangency is exactly where we're crossing through. So think about it on A, B, and C. We're crossing through exactly at the point of tangency. And then the rest of the graph is where, look at A, B, and C on graph A. They're all what we would call above that parabola. Okay? Now, let's look at C. At a turning point, maximum or minimum, the tangent is what? So think about it here. This right here was a turning point, a maximum or a minimum. And it was 0, right? So at a turning point, the tangent is 0, or horizontal. The tangent line is horizontal, right? It's flat, and the slope of it is 0. So the tangent is 0 or horizontal. At a point of inflection, concavity changes. I feel like that was bad English. Right here, for example, let's look at this graph. So for the concavity here, we are, oh, I need to go back to my pen. We are concave up, actually, and here we're concave down. Notice that the concavity changes at point A, okay? So where the concavity changes, we are going to have a slope that does not exist, okay? So you could look at it as a vertical line. But in these graphs, we don't have an example, but think about a cubic function that goes like up and then it curves like this. Isn't it possible that at this point of inflection, our tangent line would be 0, right? So there's no example that we have here, but it is possible in a few situations where you could have a horizontal, okay? So if it's a point of inflection, it's very often vertical, but it can also be 0. At a sharp corner or cusp, the tangent does not exist. So these points where the graph has a very abrupt change, there is no tangent. It does not exist. At a point on a linear function, the tangent is the same slope as the line. So basically, this whole lesson is going to be a lot of thinking through stuff like this, and so I'm not going to just give it to you every time. But let's go to example number 4, okay? Okay, on example number 4, some parts are going to be new things and other parts are going to be tying together. So I may or may not show all of my work for everything as far as live action. So look at number 4. Consider the radical function y equals square root of x. Use the difference quotient to find the slope of the curve at x equals 9. The difference quotient. Notice what it's asking us. Use the difference quotient to find the slope of the curve. That's how we know we're doing the limit. So I would go over here and make myself a little note. What am I doing? The limit I have a point. So I'm doing the function at a point. I can use this one. Remember the shorter version where we didn't have to do x plus h and all that stuff? This is the one I'm going to use because I have a point, x equals 9. And I know the function, so I can get f of a. So the first thing I need to do is just write out my formula. The limit as x goes to 9 of f of x is square root of x minus f of a. Well, this one is easy. What's f of 9? The square root of 9 equals 3. We always use the principal square root, if you've noticed so far. And then on the bottom, x minus a, x minus 9. And then we need to just go ahead and do this. What can we do? We can't plug in the 9 because we would get indeterminate form. And so we're going to have to go ahead and deal with the conjugate. So multiply the top and bottom by the conjugate. That's the square root of x plus 3 in this case. And what are we going to get? Sorry, my pen is taking up the space exactly where I need to write. So we're going to get the limit as x goes to 9 of square root of x, and square root of x is just x. Negative 3 and 3 is negative 9 over x minus 9 times the square root of x plus 3. What happens to our x minus 9s? This can cancel out with this. And we are left with the limit as x goes to 9 of 1 over square root of x plus 3. Now I can go ahead and plug in, right? F prime of 9 equals 1 over square root of 9 plus 3, which equals 1 over 6. So there is my actual answer for f prime of 9. This is not the best way to mark it, so I'm going to erase my highlighting. I didn't like that after all. So I'm just going to come over here and write it in a different color. F prime of 9 equals 1/6 because we're going to need that information. Okay. So let's go to B. Write the equation for the linear approximation of f near x equals 9. This is a fancy way of saying write the equation of the tangent line. Remember, we already did in previous lessons, we used point slope form. So that's what we're going to do. We already know that f of 9 equals 3, and we know that our m tan is 1/6. And so we can write our equation, y equals 1/6 x minus 9 plus 3. That's our equation for the linear approximation of f. The linear approximation of f means the tangent line at the point x equals 9. C, use the equation B to estimate the value for square root of 9.1. Do not use a calculator. Yes, it's for real. Don't use a calculator. So what we're going to do is we have this equation. We don't need a square root. We're using the equation from B. 9.1 minus 9 plus 3. Now I want you to pause right here and work this out, because one of the problems is that you cannot use a calculator on half of the AP calculus exam, and so you've got to get used to doing this stuff, and it's not like they give you a lot of time for each problem. So if we don't practice doing our arithmetic throughout the year, it's just going to be very difficult. So pause and then come back to check your answer. Okay, here's my work. I will tell you what I did just to give you an idea. 9.1 minus 9 was easy. That's 0.1. Then I changed it to 1/10 because it was easier in my head to do 1/6 times 1/10 instead of 1/6 times 0.1. I am aware that you could do it a different way. That's just the way that I chose to do it. And then 1/60th is what I got when I did 1/6 times 1/10, and I got 1/60th plus 3. Then in my head, I quickly said, well, 1/60th, let me change that to a decimal. 60 would go into 100 one time, so I've got 0.01, and then there would be 40 left over. So I'd be doing 60 into 400 repeatedly, because I would get 360, subtract from 40, I have 40 left over, so I'm doing 60 into 400 again, and it's on and on. So that's how I knew that my 6 is repeating. Notice that I have 3.016 and then another 6. To be honest, I'm not sure why I keep seeing on AP Calculus that they're not rounding off the last digit, but they're going out 4 digits. I am going to get us some information so that we know for sure what's the logic behind this before the AP exam, but for now, I'm just going to follow the suit of everyone else doing it this way, okay? So now graph the function and its tangent line at x equals 9. Okay, so we need to first graph the function. So if I look at this, square root of 0 is 0, square root of 1 is 1, 4 squared would be 2, 9 would be where 3 is, 16 would be at 4. So this is the function, right? Square root of x. And then, and I barely missed that point. There we go. Then it said to also graph the tangent line. So that's going to come through here. Oh, I can't seem to do it. Here we go. Let me try again. I feel like I'm not very good at drawing the tangent lines, but this is close enough. I didn't mean to select it. So here's our tangent line with the arrows. Explain whether your answer to C is an overestimate or an underestimate for the actual value of square root of 9.1. So thinking about, based on the graph, justify your answer by reference to the behavior of the graph. I want you to pause and think about this again. Why would your answer be an underestimate or an overestimate? Look at the graph, look at your answer, think about what you know so far about the tangent line, think about all the things we talked about. If you're still not ready to pause, just give it a moment. I'm not ready to tell you the answer. If you're still not ready to pause, I'll give you another hint. Think about what we talked about on the page just before about concave up and down, and that the tangent line would be above the curve or under the curve, that sort of thing. And then decide what is your answer to this question. Okay, 3, 2, 1. Okay, here's one possible answer. It is an overestimate because f of x is concave down and the tangent line lies above the function. If the tangent line is above the function, then that means the y value is going to be slightly higher. It might be like 1/1000th or 1/1,000,000th. It could be any tiny piece. It could be 1/10th. But it's going to be higher because the concave down means that the tangent is going to be above it. Another thing that you could notice, if you think about it, the graph, the orange graph, the slope it's an increasing slope, meaning it's moving up, but the actual slope of the tangent lines would be getting closer and closer to 0. Because think about it, this is going to be going further and further. The orange graph is going to be going further and further to the right in between points. So like here, the tangent line, let me get a different color. The tangent line is like this, and it's gradually getting, even here, it's going to keep getting flatter until eventually it seems to be almost a completely horizontal line. So in that regard, the slopes of the tangent lines are decreasing. The slope of the curve is actually decreasing as it moves to the right. That's another way to explain it, but saying that it's concave down and the tangent line is above it is actually probably the easiest way. F says find the true value of square root of 9.1. Put it in your calculator and see what it says. Do it. You can do it. 3, 2, 1. Is there a reason that I went so many decimal places? Sorry, I dropped my pen. There is not a reason. I just went farther out. It would help us to notice in our answer that we approximated, or at least in mine, I got a repeating 6. Look how close that is. We went all the way to the 5th decimal place before it changed. So that is pretty accurate, even for doing it without a calculator. So, would your linear approximation formula be an accurate tool to estimate square root of 25? Why or why not? This is a very important question. Please pause the video. Think about everything that you know so far. Why would they ask you this question? Is this an accurate tool to estimate square root of 25? Why or why not? This is where the Jeopardy music is playing. If you haven't paused yet, I'm still waiting. And if you have paused and you've come back now, just fast forward a bit or put it on double speed and I'll be done dragging this out in a minute. Think about what was the original function, square root of x. Think about why did we do x as 9 or 9.1. Think about the whole point of this lesson, linear approximation, local linearity. Go back to the very beginning. There's vocabulary at the very beginning of lesson 3. Okay, here comes my answer. No. X equals 25 is not in the local neighborhood of x equals 9. It is too far from the point of tangency. If you had used square root of 25, so no, square root of 25 is not in the local neighborhood of square root of 9. That would still be correct. I just said x equals 25 because that's what they put here for square root of 25. Remember, the point of this whole lesson is linear approximation. You have to be in a sufficiently small neighborhood at a point. This entire problem that we did on this page was at x equals 9. 9 and 25 are pretty far apart. That would definitely not be considered a local neighborhood, okay? Let's go to example number 5 now. This is going to be another one where I'm going to let you do some of it on your own, and I need you to just remember what we already talked about, that the tangent lines are very difficult to draw. And so getting the slope from the graph is going to be an estimate, okay? So let's read this first. We know that the derivative of a function at a point represents the slope of the tangent line at the point. Estimate the value of g prime of x, remember that's the value of the slope of the tangent line, for each x value in this table by drawing a tangent line through the given point of tangency. Then estimate the slope derivative at the point. Find the y-coordinate of the point of tangency and use the point-slope form of an equation to write the equation of the tangent line at the point x equals a for each x value. Okay, here is the formula for tangent line approximation of f at a. I apologize, I thought that was my highlighter. F of x equals f of a plus f prime of a, parentheses, x minus a. It might not look like it, but this is actually basically going to be the same thing that we did with point slope form. It just looks slightly different. So here's what you're going to do. X equals a. It says x is -3. So you come to the graph, -3. They're talking about point A. So you need to use a straight edge to draw in the line of tangency, and then estimate what is the slope of that line. The derivative estimate, remember the derivative is right here. We know that the derivative of a function at a point represents the slope of the tangent line at the point. So where it says to get the derivative estimate, it means to find the slope. I just accidentally hit the erase button. The mtan is the derivative estimate. The point of tangency is the actual point that you started with. The function behavior, they're just wanting to know, is it constant, increasing, decreasing, etc. And then write the equation of the line. So the first thing I would recommend that you do, look at the first one, and then I would recommend that you find your slopes, because remember, they're going to be estimates. It's entirely subjective. You do not have to have the exact answer that I put in, okay? So go ahead and look at x equals a for -3. So right here, go ahead and draw your point of your line of tangency. Sorry, your tangent line. Here's my line. I am going to estimate, I crossed this point right here. How far is that? 1, 2, 3, 4, 5, 6 over 1. So I'm going to give a derivative estimate of -6. That just means that I'm saying that my slope is -6. What was the original point? It's -3, -3. I'm just going to write that in. What's the behavior function? Look at the original graph. What is happening to this graph? Well, we said the slope is negative. Doesn't that mean that the graph has to be decreasing? The slope of the tangent line is negative. If we look at it, it makes sense. The graph itself is moving down from left to right. The equation of the tangent line at x equals a. If I were writing it the way that we normally do, we would have -6 times x plus 3, because remember on the x we changed the sign, and it would look like this. If you wanted to put it in this order, it would look like y equals -3 minus 6 times x plus 3. Notice the only difference is that we normally have plus y at the end and there's nothing in the front. You can do it the same way we've been doing it. There's no need to go and change it, but I just wanted to show you that on the first one. So my recommendation right now, if you're just watching the video, is to do one of two things. Go ahead and draw all the tangents and figure out the slopes, and then come back and do the point of tangency, the behavior, etc. And that way you can check your slopes with what I have before you fill in the whole table. if that's really going to bother you to have a different answer. Okay, so I'm going to just give you what I got for my derivative answers. I'm going to fill in this column first. Okay, first I'm waiting for you to pause. I'm still stalling. All right, we've stalled long enough. Here we go. Here's what I got by estimating, drawing the line for each point that they asked us for X value. I drew the line of the tangent line, and so that's what I got. This is subjective. If yours is close, if yours is a little bit off, you can change it or you can leave it. Now, please continue to do the point of tangency, the function behavior, and the equation of the line. I'm about to give you the second one, so pause and make sure you've done it before you look at your answer. Okay, there's the second one. Pause again if you want. If you haven't done the third one, you could just do them all and then just watch this video in double speed and be done. Okay? Okay, here comes the third. All right, 3, 2, 1, here comes the fourth. Okay, on this fourth one, keep in mind that if you estimated that the y value for 1.25 isn't exactly 1, you would just have y equals whatever you got for your y value, and that's fine. Okay, here comes the last one for x equals 4. Okay, here we go. That was all of them. Now remember, keep in mind, if you got a little bit different slope, it's fine. No big deal. Or derivative as it is in this case. Let's go to the next one. We're getting nearer to being finished. Investigating slope graphs or f prime graphs. Now here's the part where it's going to be even more, I won't say subjective, but a little bit. You got to think more about the terminology and just process. So you might need to pause and rewind and rethink as we go through this section. That's okay. Okay, if you've already taken physics, this part might sound a little bit more familiar. If you haven't, it's fine. I'm not going to go into an extreme amount of explanation because if you haven't taken physics, I'm not going to be able to successfully explain that. And I'm not a physics teacher. I'm not a person who particularly enjoyed studying physics. So I might not be the best person to try to explain it to you quickly. So let's just look at the information that we have and then see how does this affect us with our graphs. So when you plot the motion of an object as velocity versus time, these are referred to as slope functions or f prime graphs. So you read that as f prime as usual. In the study of calculus and physics, these graphs represent the rate of change of the original function. By analyzing these graphs, you can find where changes are occurring slowly or quickly by observing the rates of change or slopes of the tangent lines at specific moments in time. Okay, so the key thing is to notice it's the f prime graphs. Remember velocity, if we flash back to earlier in AP Calculus, we talked about that velocity is basically like the derivative, or it's the taking the tangent lines and making a graph out of the slopes of the tangent lines. So let's just look at an example and it'll probably make more sense. So consider the function shown at right. I'm pretty sure this is at the left, but okay. Notice the curve at the first point, x equals 1/2. The slope of the curve here appears to be about 1. So they're talking about this red line. The slope of that red line appears to be about 1. Then at x equals 4, the slope of the blue line has decreased to about 1/3. Can you analyze and sketch the slope graph on the grid below? Here's the deal. We could probably try to calculate it exactly or use the points and figure it out, and it might not match. Again, that's not the point. They gave us these points, so let's just use them. We know we can draw the graph from that. We've got the point 0.5 and 1. So x is 0.5, y is 1. When x equals 4, f prime equals 1/3. So when we're at 4, we're down here at 1/3. Okay, and then what's happening? We can see that our graph started at 0, 0, the black graph, right? The original function. And so we're just going to have our curve coming from 0. And then what's going to happen as this continues? It's not going to go, oh, I moved my pen just right. It somehow thought I was trying to, okay. I'm going to have to erase this line and do it again. Let's just draw a line like this. It's not going to cross the 0, okay? This is our reasonable estimate. Okay, so what is the point of this? Here, this is our f prime graph. We have graphed the slopes of the tangents, okay? The slope of the red line made our first point. The slope of the blue line made our second point. The x value and then the slope of the tangent. The x value is the x value in the original function, and then the slope of the tangent at that x value. So let's come down here and look at another example. Compare the graph of f to the graph of f prime. So notice this is f prime, okay? Now, the f prime graph, I'm reading down here now, the f prime graph gives us insight into the behavior of the original function. For example, at x equals 1, the slope on y equals f of x appears to be almost negative 2. Let's pause and look at that. X equals 1, we're right here, and the slope is coming down pretty steep, and if you think about it, this point of 2, 0 is pretty much spot on. So that gives us a good idea that the slope of that is about negative 2. Therefore, on the y f prime of x graph, the value at x equals 1 is almost negative 2. So here, x equals 1, we're right here just above negative 2. It's almost there. There are several relationships between the two graphs that are particularly important to note. Let's explore these features in depth. So here's the problem. I'm going to have to go back and forth between this page and the next because it just doesn't all fit on my screen. So I apologize. Hopefully it will still work out for you. Okay? Investigating slopes continued. When the graph of a function is rising, we will say that the function increases, and when the graph is falling, we will say that the graph decreases. It is customary to read a graph in much the same way as we read a book from left to right. So starting at the left on the graph of y equals f of x, state the intervals of x where the graph rises. So we're just looking for where is the graph rising from left to right. So let's go back. And okay, just to be clear, we're looking at the graph of y equals f of x. Where is it rising? So here, this is definitely, let me change colors. And I'm going to erase this line that I drew the first time. Okay, so I'll use this color for now. This part of the graph is rising, right? And then again, we have a section right here that would definitely be increasing. This we could think back to even algebra 1. An increasing function, it is increasing when you go from left to right, it continues to go up, okay? So these two are our sections where it is increasing. And the question said, what do you notice about the slope of the curve on these intervals? What do you notice about the slope of the curve? Okay, so first I'm going to try to figure out what is the interval. This one right here maybe stops. I'm going to just say -1. It's close enough for me. And then this one is a little bit off. So I'm going to say like 4 1/4, something like that. So first, let's write our intervals of increasing or rising down here. Okay, here's our two intervals. From -infinity to -1, it's rising. And from 4.25 to infinity, it's rising. So looking at the graph, the slope of the curve, not the tangents, it's the slope of the curve. The slope is doing what? Okay, the slope of the curve is positive here. And I'm sorry I wrote that in cursive. I have a habit of doing that. The slope of the curve is positive here. This is true. That's what it means to be increasing, right? Or rising. Starting at the left, state the intervals of x where the graph falls. What do you notice about the slope of the curve on these intervals? Well, let's think about it. This section in between here is when it's falling. So we can just know that it's the interval from -1 to 4.25, right? The interval between these two increasing intervals. And so what do we know about that? It's decreasing. And I didn't write out the first one, like full complete sentence style. I'll do that this time. Okay, here's our two answers. F of x decreases on -1 is less than x is less than 4.25. The slope of the curve is negative here. So from the beginning, on the first question, I could have written out a sentence about increasing. Let me do that real quick. So if you wanted to see how to write out the interval for A, f of x increases on -infinity is less than x is less than -1, and x is greater than 4.2. So these are our two increasing and decreasing sections. At what values of x on the graph of y equals f of x does the function appear to have a maximum or minimum value? Let's go back and look at it. We're looking for maximum, minimums, and then it says what is the slope of the curve at these points? What characteristic of the f prime graph occurs at these points? Well, that's a lot to look at. First, we're looking for maximums and minimums. Changing my color again, we can see that there is a maximum here and a minimum here. Interestingly enough, it's right at our points where we change from increasing to decreasing, right? So we've got the point here, -1, 4. It looks like it's about 4 right there. I might need to, let me just do a little bit of erasing. It's above 4. So I'm going to change that to like 4 1/4. -1 and 4.25. And then down here, let's look at this part real quick. We're coming just above -3. Okay, so this one is like 4.25 and -3-ish. So I'm going to call it -3. And realistically, we're really just focusing on the x value, but that's fine. So let's go back and look at these on the other page. So what do we see? These are maximums and minimums. I'm going to write that down now. Okay, here we go. F of x has a relative maximum at x equals -1 approximately, and a relative minimum at approximately x equals 4.25. What happens to the slope of the curve here? Nothing really, right? It's 0. The slope of the curve is 0 at these points. Okay, the last one. What characteristic of the f prime graph occurs at these points? Let's go back. What do you see right here at -1? What do you see right here at 4.25? Those are zeros, right? The relative maximum and minimum made a 0 on the prime graph. This is very important. On f prime of x, these points are zeros. If you don't remember, that means they're x-intercepts. Okay. Now, D, look carefully at this one. Why does the graph of f prime of x reach a minimum value near x equals 1.5? Can you explain what is occurring at x equals 1.5 on the graph of f of x to create this minimum on the slope graph? Let's go back. So right here, we have this minimum at about like 1.5-ish. What's happening on this original graph at about 1.5-ish? For the sake of looking at the graph more cleanly, I'm going to erase all of my drawing. What happens here? I feel like this one is a little bit harder to see, but remember we talked about this is concave down and this is concave up. The question is, where does it really change from being concave up or down? And what is hard to see is that it's actually going to be somewhere around here that it changes. And if you think about it, here's 1, here's 2, you're in between there. So that's what they're getting at, is that this is where it changes from being concave up or down. Notice right here, concave down, we're on this side, we're decreasing. Concave up, we're increasing. Okay? That's an important detail of the graph of the prime. If it's an increase, if it's concave down, the graph is decreasing. If it's concave up, the graph is increasing. So we can come back down here and write what is happening to the graph on D. What's going on about x equals 1.5? At x is approximately 1.5 on f of x, the graph changes from concave down to concave up. Okay, that's what caused it to switch directions. So here's some more notes. Procedure to sketch an f prime of graph. 1. Describe how the slope changes from left to right along the curve. Is it increasing or decreasing? Notice the intervals where the slope is positive, negative, and 0. Positive slope means it's increasing, negative slope means it's decreasing, 0 means it's constant. Write down the changes as they occur from left to right on a number line. Notice where the x-intercepts occur. Pay attention to where the function is above the x-axis, positive and where it is below the x-axis negative. We didn't actually talk about that, but let's come back and look real quick. Notice here on the graph, let me change colors. I'm going to erase and get a different color. So on this part of the graph, slope is increasing. Remember, we said it's going up, and I did it again. Slope is going up. Notice it's positive. We said already that the zeros are the maximum and the minimum, right? So this one is positive and this one is increasing, and we're above the x-axis also. Notice that for this part where we are decreasing, we are below the x-axis. That is always going to be true when you're graphing the f prime. You're graphing the function that's representing the derivatives or the slopes of the tangent line. If it's an increasing slope, you're going to be above the x-axis. If it's a decreasing slope or a negative slope, you're going to be below the x-axis. That's where the positive and negative y values come from. So let's run on down to this example. And I'm afraid if I just do this, you're not going to think it through on your own. And the video is getting kind of long. So all I'm going to do is tell you to pause, and then I'm just going to work through this thinking it out loud, and that's going to be it. Okay, so here's what's going to happen. I'm looking at the graph here. It's decreasing until about this point. So down here on this number line, they gave us this because we're saying this is one of the changes in positive, increasing, decreasing. They gave us this to post plot it out. Here, it's going to start decreasing again, and I don't remember if I said that was increasing or decreasing. It's decreasing on this side, and then we come over here to positive 3, and it starts decreasing again. In between there, I'm increasing. So this is an interval of increasing, okay? So remember we said that those max and mins are going to be x-intercepts on the x prime graph, right? And so I already know that my points on the graph, I'm going to have -2, 0, and I'm going to have 3, 0. Okay. We also said that when it's decreasing, I'm going to be in the negative. So this section, I'm going to be down here. This section, I'm going to be down here. And this section, I'm going to be in the positive. So we at least know that much already just from having those two pieces of information. Okay. So one way you could put it is that these are negatives and these are positives. And these are negatives again. And then also looking at concave up or down. This part of the graph right here is concave down. So I'm concave down on this side. And then somewhere in here, maybe here, I don't know. Let me change colors again. Maybe like right here, I'm going to switch over and become, I said that backwards. This side is concave up. Look, it's opening up. So here we have concave up and down. Since it's not exactly at 1, I put 0.8. This is going to be a maximum or a minimum. Which one? Well, I'm going from decreasing to increasing to decreasing. So I'm going from negative to positive back down to negative. So this is going to be a maximum. Okay, so basically what's going to happen is that somewhere around 0.8, we don't really know what's the y value, but I'm just going to put it up here somewhere. I don't know. It's going to be about right there, and this graph is going to go like this. How do I know all this? Just from the information that we already figured out. Okay, so this is a reasonable estimate of what the graph would look like of the g prime function. And we can come down here and answer these questions. Mark the number line above to show values where g of x changes from increasing to decreasing. We already did that. At these values, x values, the slope of the curve is 0. On the function, we refer to these values as maximum and minimum. Okay. Notice how the graph changes from concave to up or down. That's your point of inflection, okay? And use your summaries to create the graph. That's what we did. So we did it before we read the directions. And there is one more page. We've seen that it's possible to estimate the numerical value of a derivative at a single point by finding the slope of the secant line passing through 2 points on the graph. Let's explore how this can be done using a table of values for a continuous function. Let me zoom in a bit. So I just want to point out in your mind, think about this. If you have a graph, we've already talked about the slope of the secant line would be connecting 2 points. The tangent is when we're getting closer and closer to 1 point. So thinking about this table, if we have our points, let's say right here, x equals a is -2. So we have a point for -2. We are not going to use the value at -2. We're actually going to use the closest values above and below it. The reason we're not going to use the exact one is, think about this. If I have a curve, some sort of curving line, let's not make it look like a quadratic, just a curving line. And let's say that this point here is -4 and this point here is -1. If I connect them, then I'm going to get the actual slope of that line. If I try to go over here to -2, notice how different the two lines are. The one in the middle is going to work better. So try to visualize that, draw yourself a little picture if that didn't make sense. Let's go ahead now and look at what we're doing. The math is going to be the easy part. All you're going to do is use the slope formula for the two closest points. So for example, when x equals -2, we're going to take the 2 points I've already highlighted and we're going to do the slope formula. 4 plus 6 over -1 plus 4, which is going to give us what? 10 over 3. So f prime of -2 equals 10 over 3. It says, what's the function's behavior? Well, if this is the slope and it's positive, what does that tell us? The graph is increasing. Remember, if the slope of the tangent line is increasing, is positive, then the graph is increasing. So the justification at the point -2, 2, f prime of -2 is greater than 0. That's our justification for saying that it's increasing. What are you justifying? You're justifying that we said it's increasing. Let's look at the next one. I'm not going to work out each one piece by piece. I'm just going to get you going, and then that will be enough. So looking at x equals -1, that's right here. So your 2 points closest to it are 0 and -2. Go ahead and do your slope formula. All right, this time we got -3 over 2. What does a negative slope on the tangent tell us? That the original function is also decreasing. What's our justification? F prime of -1 is less than 0. And we should go ahead and write our x point at -1, 4. F prime of -1 is less than 0. Keep going. This time I'm going to have you do x equals 0 the entire way and then come back and watch. So this is where you should pause the video. Okay, 3, 2, 1. Okay, here we go. We got a f prime of 0 equals 0, so it's constant, and our justification is that the slope of the tangent is 0. That means that the graph is probably at a maximum or a minimum, right? Relative max or relative min is where we end up with a 0 on the f prime. All right, do the next one. In 3, 2, 1. Okay, here's this one. We're increasing again. We got f prime of 2 equals 1. It's increasing. Your justification is that at 2, 4, f prime of 2 is greater than 0. Okay, last one. 3, 2, 1. All right, here we go. I do want to point something out to you. We talked about right here at x equals 0, we had a constant. And I made the statement that that means most likely there's a point of relative or minimum relative minimum or maximum. Well, one thing I want to point out is notice that before the constant it was decreasing, and after the constant it's increasing. That tells us what? If we go from decreasing to increasing, what happened? That would mean that there was a relative minimum, right? Because think about it, you're decreasing and then you start increasing. That means there's a relative minimum, okay? So we've done all of those parts. Let's come down here and look at some facts and findings. Please think through this on your own instead of just copying my answers. This is where you pause and think through it on your own, okay? Just pause and think through it for a minute and then come back to it. All right, if f prime of x is less than 0, then the graph of the function is decreasing We've already made all these justifications, so you should have got that. Decreasing at x equals a. If f prime of x is greater than 0, then the graph of the function is increasing at x equals a. This last part is two statements. Number 3, a relative maximum occurs on a function if f prime of x equals 0 and the derivative changes from increasing to decreasing. So when we change from increasing to decreasing, think about that. We're increasing and we start going down. That's a relative max. What's going to be a relative minimum? It's going to be the opposite, which we just looked at an example. F prime of x equals 0, and we go from decreasing to increasing. Okay? So that is all of the information for this lesson. I do feel like earlier I was trying to give you this example about why we use 2 points. Let me do a better job with some color. So let's say that I had -2, 2, and this is going from increasing to decreasing, right? So at -2, it's increasing. And then somewhere it's going to start decreasing when we get to -1. So if I was at -2 right here, and I used the point for -4 and -2 to find the slope, it looks like this. Okay? If I used the point for -1, it looks like this. Okay, so this is my point at -1. This is my point at -4. Notice that the pink and the green line are like really bad. They're not estimating the curve. If I had my line, let me draw it in a different color one more time. If I had my line here in orange, think about that. Okay, I'll erase. That wasn't good. Connecting these 2 points. This is closer to the tangent here. This is a closer line than the pink or the green one. So that's why we're using the 2 nearest points, okay? Because you're getting a closer approximation to the actual tangent line instead of 2 totally different slopes, okay? So that is what we're looking at. Thank you so much.